It's my great pleasure to introduce Sharon Goldberg today. She has a very interesting history coming from both theory and systems. Back from her PhD work, she was supervised at Princeton by Boaz Barak and Jennifer Rexford, which is an interesting mix of those of you who know them. After a postdoc at Microsoft Research New England, she is now at Boston University, so stayed local for us, and continues to work on both systems problems and theoretical problems. You're likely to find her work at SIGCOMM or at SOTA or a crypto conference. So she's going to be talking to us today about some of her work. Some work, I'm happy to say, she actually did with one of my ex-students now, as well. So big welcome for Sharon Goldberg. Thanks.
Okay, so you've all seen my shameless plug. So the talk today is about the adoption of new technologies in the internet, and actually one of the things I've been working on for years is the adoption of new technologies in the internet, and one of the things I realized is one of the reasons why technologies often have difficulty being adopted, apart from the reasons I'm going to discuss in this talk, is because network operators are actually concerned that they're going to make it easier to do censorship and blocking, and so I've actually been working on these issues as well right now. And with Nick Feimster, we decided to organize a local day. So David Parks is not here, but he organized Cake with some other folks, which was a huge success. So basically, we're doing a complete rip-off of his idea, but doing it on this topic, so I hope you'll all attend. Okay, so that's the end of my plug. Now for my talk. So this is joint work with mostly Zhenming Liu, and then another paper with Philippa Gill and Michael Shapiro. So this is a tale of two protocols, so I need to tell you first about the two protocols. I'm going to be talking about two protocols, IPv6 and BGP-SEC, and talking about the difficulties in getting these adopted in the internet. So first of all, IPv6. Probably people have heard, the sky is falling, we've run out of IPv4 addresses. And what are IPv4 addresses? So basically, when we do communication on the internet, we use this protocol called IP, the Internet Protocol. And roughly, all we need to think about right now is the fact that every time we send a message, it has a source address and a receiver address. And the address is 32 bits long. Okay, and this is how the internet was designed, back a long time ago. And they thought that 32 bits would be enough. But if you actually work out what 2 to the 32 is, it's 4 billion, which is about half the population of the world. So you can imagine that that's not going to be enough addresses for us. Now, in 2008, internet engineers realized, in 1998, internet engineers realized that this was going to be a problem. And so they actually completed the standardization of a new protocol to solve the problem of the fact that we were going to run out of IP addresses. Back in 1998, their solution was to create a new protocol that instead of having 32-bit addresses, now had 128-bit addresses. Okay, that's what IPv6 does. That's pretty much it. Now, we ran out of IPv4 addresses in 2011 for the global pool. There's still a North American pool. That pool is set to run out in 2014. And so, there's been a slow push towards IPv6 adoption. I can show you. Here's an adoption curve. Okay, so as of today, which is 15 years after the standard was proposed, 1% of the internet around, from Google's perspective, is using IPv6. Okay, so that sounds like not too much. But I was actually, when I saw this number, I was very excited. To me, this number is very high. Because you can see it's taken off. Because if I'd given this talk 2 years ago, we would have been here where it would have been oscillating around 0.2%, and it wouldn't have been moving very much. The past few years, it's actually increased a lot because there's been a huge PR campaign on the internet to actually get this deployed. Okay, so this has been slowly happening, and we'll talk a little bit about why things have actually been moving in this direction with IPv6. But for a long time, it was like sort of not moving at all in terms of adoption. Okay, the second protocol I want to talk about is called BGP-SEC. BGP-SEC secures internet routing. So to understand how it secures internet routing, just briefly of how internet routing works, this is hugely oversimplified. The way the routing protocol works on the internet is there's this idea that all routing messages should be trusted. So for example, when YouTube wants people to route to its IP addresses, it just sends a routing message saying, if you would like to reach YouTube IP addresses, this is how you do it. Okay, so it's just basically this message, and then the internet routes in that direction. The point is this message is not authenticated. There's no sort of reason for anyone to believe that these addresses should actually be where you're saying that they are. And this can be exploited with pretty horrible effects. So here's something that happened in 2008. This other network It's interesting, this actually happened because they were trying to censor the addresses and things got out of control. But what they were doing was they just claimed that they owned YouTube's IP addresses. And the way that routing works and the way that they actually claim this, the result was the entire internet routed to Pakistan Telecom and all of the YouTube was taken down. So it sounds kind of silly like, oh, okay, so YouTube was taken down, so what? But actually what's important about this is that you have this system that was built and engineered to be highly redundant, highly available, multiple data centers all over the world, you know, low latency and everything like that, and the system gets completely taken down simply because some network that's completely unrelated to it, like Pakistan Telecom, just claims to own their IP addresses, and the entire internet believes them and routes in that way. So this is one of the reasons that routing security is considered to be a really important problem by internet engineers. Okay, so people were aware of this. Back in 1997, this protocol called Secure BGP was proposed and was standardized. The standard was a failure, I guess. I don't know if I want to say that, but it wasn't adopted by anyone. And now, as we speak, there's a new standard being proposed for BGP security that actually takes into account some of the reasons that the standard from 1997 didn't work out too well. Okay. So these are the two protocols we're going to talk about. Let me quickly show you how BGP-SEC works. So the first thing that happens is that there's a public key infrastructure. Each one of these nodes, so we can think of the internet as a graph. Each node is called an autonomous system or an ISP, an internet service provider. You can think of each node being run by a different company, like YouTube. Here you have two internet service providers. What happens is that each one of these gets a key, and now whenever they send a routing message, they're actually going to sign it with their key. Okay, so now when YouTube claims to own its addresses, it's signed by YouTube's key, and one can verify that this was actually said by YouTube. Again, I'm grossly oversimplifying how this works, so if you want more details on how this protocol works, I'll tell you after. But as the protocol proceeds, what happens is that each time you get a path through this network, each node on the path is going to actually sign that they're on the path. Okay, so now you can't have a node coming out of nowhere claiming to be on the path when they actually aren't. Okay, and the way this is done is through this public key infrastructure here and these signed routing announcements. Okay, so if you don't quite understand why this secures the system, I'm glossing over things and I can take some questions on that afterwards. Here's the point though. Why is the transition here so difficult? So there are a lot of reasons why it's difficult, but there's one fundamental thing that I think is common to a lot of these network protocols that makes it difficult to deploy them. For each one of these protocols to work, it has to be used by all the nodes on the path. So here's a graph here, and where the dark purple nodes have upgraded to the new protocol, and the purple nodes have not. So we can imagine that the dark ones are using IPv6, and the other ones are using IPv4, for example. So the way these protocols work, IPv6 is actually a really interesting protocol. It's completely not backwards compatible. If you give a device that only speaks IPv4 an IPv6 message, it'll drop it on the floor. It doesn't know how to read it. It just gets completely dropped. And so you can't actually send messages through a network that doesn't, you cannot send IPv6 messages through a network that does not speak IPv6. Similarly with BGP-SEC, actually BGP-SEC was designed later, so it's not quite as not backwards compatible. It's actually very backwards compatible, but the way it does backwards compatibility is as soon as there's someone on the path who doesn't speak the protocol, you just send the message in the old format, in the unsecured format. Okay, so for example, if you sent a message on this path here, all of these networks have keys, they all speak BGP-SEC, and the message will be sent via BGP-SEC. But if we were to look at this path here, there's a node on the path, two nodes on the path actually, that don't speak BGP-SEC, and so the message will be sent in the old format, the insecure format. Yeah?
So why are the nodes full ISPs rather than different classes?
Right, because what we're talking about today is incentives for adoption, and you should think of these nodes. These nodes are, we're going to think of these nodes as agents. They're going to be economically motivated agents. The reason that we're looking at, so it's true, a node has hundreds of thousands of routers in it. It can be a huge network like AT&T, and we're going to just think of it as a node. But what we're trying to do is look for incentives for these autonomous systems, these ISPs, to upgrade their networks to a new protocol. And since we're looking at incentives, we're going to look at the level of the organizations that control these networks. Okay, so inside here we have small routers, but they won't matter for us. Yeah.
So what does BGP-SEC do if there are multiple paths, some of which are good and have all the all the nodes have upgraded other ones? Is that a way of detecting that they're...
No. So this is a very, very complicated question. We actually just submitted a paper to SIGCOM to answer this question. So let's imagine that we were trying to communicate with this node right there with the turquoise key. The node at the top, let's say the one with the red key is trying to talk to the one with the turquoise key. It looks, if we just look at this at a high level, we might say, he should take the BGP-SEC path because it looks better, because it's secure, not the other path. The thing is that the routing is very complicated in these networks. So for example, it's possible that the node that's insecure is actually a cheaper route than the node that is secure. And so the decisions that a node is going to make are going to be very complicated. They're going to be based on security and actual costs of paths. Whereas cost of paths with BGP is done on a per edge basis, not on a path basis. But anyway, yeah, there are a lot of considerations that come into play there. What the standard says is you can do whatever you want. So you're not required to pick
It would at least know, it would at least be aware that there is a better path, and then could decide not to use it.
Well, okay, so basically what happens is that let's imagine that that red node is trying to decide how to reach the green node. He would learn two paths, a secure one and an insecure one, and then he'd have to choose one. So basically you learn paths from your neighbors and you look at those paths and their properties. You might have a secure path, you might have a neighbor that's cheaper, and you make a decision based on those things. Yeah, so it can be very complicated, yeah.
If there is a path with, let's say, first 100 nodes are secure, they do a BGP-SEC, and then the last one doesn't. We do all the work through the beginning and then find out that it doesn't involve BGP-SEC.
Yep.
It is very inefficient.
Yep. Yeah, that's what it does.
So learn in advance that there is a node in the path that doesn't speak BGP-SEC and not free.
Yeah, so it was designed to be as simple as possible. So the way the protocol works is it's just messages propagating. So there's the route that you're all trying to reach, and the messages propagate outwards from there. And it's really just, you learn something, you tell your neighbors. You learn something, you tell your neighbors. They don't want to have multiple rounds of learning things, so that sort of thing would be very complicated to implement. So really, every node learns paths from its neighbors, makes its own local decision, and then passes that on to everyone else. So yeah, if there was one node right at the end here, that somehow, imagine you had a whole graph and then there was one node here and then the rest of the graph. That node doesn't speak BGP-SEC, that's it. It's all stripped. There's no way around it. And actually, I was in the room when they were doing this, making this decision for the standard. And one of the reasons was they were saying, tell me from a security perspective why this helps me. And nobody could make a compelling argument why it helps from a security perspective. It just made things more complicated, and so they decided not to do it. Yeah. Questions? Okay, so this is these are the two things that we're going to focus on today. The fact that in order to actually use the protocol, you need to pass through the network of people that use it. And also that these nodes are economically motivated agents. They're owned by organizations that are there to make money. And even if they're not there to make money, if you deploy IPv6 and you're the only person in this whole network that uses it, then you can't talk to anyone using this protocol. It's of no use to you, right? You need to actually be able to talk to someone in order to use this protocol. And so those are the two issues, sort of like a chicken and egg problem. You can't use the protocol until you have people to use it with, and you can't really use it until there are these paths. So this is the problem that we're going to study. I'm going to talk about two papers. I probably won't have time to do both, but we'll see. In the first paper is a paper I wrote with Zhenming Liu, who was Michael's student. And I wrote it with him while he was Michael's student. So while he was here at Harvard, which was a really great collaboration. And what we are doing in this paper is we're assuming that nodes want to use this protocol because they actually want to use the protocol. So for example, BGP-SEC brings them some value. It's security. They want security. They want to use BGP-SEC. Or IPv6, they would like to have a lot more addresses than what they already have, and so they would like to use IPv6 so they can communicate with it with more nodes in IPv6. This second paper we wrote was this SIGCOMM 11 paper that I wrote with Philippa Gill and Michael Shapira. And what we do here is we're much more cynical. We say that these nodes actually don't care about the protocol. All they want to do is make more money. So the idea is I'm going to adopt a protocol, and somehow because I've adopted this new protocol, I am more attractive to my customers, and therefore I'm going to make more money. Okay, so in both of these papers, we use this idea that you need to actually, that nodes are economically motivated and they need paths through the network in order to use the protocol. But this one is a much cleaner formulation, and this one is a lot more difficult and delicate. So I'm going to talk about the first paper because this is the most recent one. Okay, so we have a very simple model for technology diffusion. Okay, so here's our model. We have a graph. The graph has nodes. Each node is an ISP. Now the ISP wants to adopt the protocol, and he says that he's going to adopt the protocol if he can use it to communicate with at least theta other ISPs. So let's look, for example, over here. This purple node is trying to decide if he can adopt the protocol. So the utility he gets from the protocol is proportional to the number of people he can talk to using the protocol. So if these red people have adopted, red ISPs have adopted, these ones have adopted, but these ones have not. So he can communicate with this one, this one, this one, this one, and that one using the protocol, but these three, even though they've adopted the protocol, that he's not able to reach them via a path that uses the protocol. So his utility in this picture will be 5. Yep.
Is theta the same bottleneck?
Okay, so in this model, the theta is going to be different, and in fact, I've actually written them over there. So the red nodes have theta of 1. The turquoise nodes have theta of 11 over here. So we're going to assume that they have different thetas. In the second paper, we actually assume they all have the same thetas, but this one. Okay, so we have this model of utility where utility basically is the size of the connected component of active nodes that you're adjacent to. So in this case, this guy's adjacent to a connected component of size 5 active nodes, and so that's going to be its utility. And if his utility exceeds his threshold, then he's going to adopt the protocol, and if not, then he won't. Yep.
So there's no form of risk neutrality or risk aversion that's difficult to.
I guess not. I'm not sure how would you think of risk of neutrality?
In a sense, since it's a linear utility function, as the number of nodes increases, it's going to linearly increase.
Yeah, it's actually related to the linear threshold model, which we'll talk about in a second. Okay. So in this paper, what we're doing is we're trying to solve the following problem. We're trying to figure out which nodes should be early adopters of the protocol so that we can drive adoption through the whole network. Okay. So first of all, what do we mean by early adopters? So early adopters are a set of nodes that can kick off the process. And actually, in the setting of routing protocol adoption, this is, in my opinion, exactly the right thing to think about. Because if you look at what happens in practice when they're trying to deploy these new protocols, they try to get large networks like Google and Akamai and AT&T and things like that on board with adopting the protocol first. So once they do it, the smaller networks will actually follow suit because they've seen the larger networks do it. So the question that we're trying to address here is, given the graph, which should be the networks that should first adopt this protocol? And the way this works is if we have this purple node be in the seed set, for example, and this blue node be in the seed set, there's going to be a process of diffusion through this graph where these red nodes just turn on because their threshold is 1. So they're adjacent to an active node. So all of these guys turn on. It turns out that it stops here, but if I add another node to the seed set right here, then these orange nodes now have, these orange nodes are now on, and so on, and it propagates like this. Okay, so each different colored node has a different threshold, and they're going to activate as long as they're connected to a component that's bigger than their threshold. Questions? Okay.
So just to clarify, when you say activate, you're just saying that it's adopting the new
Yeah. So sorry. So the term activate means adopting the new protocol. Okay, so here's the problem that we solved. Given a graph and thresholds, what's the smallest seed set that can cause the network to adopt? Okay. Now, this problem may look familiar, and it's inspired by 2 different pieces of work. I'm going to actually put everything up at the same time. So there's 2 pieces of work. Maybe I'll start with the second one. So the second one, I think, is familiar to most people here, is this notion of local network effects. So what you were thinking of here is we have some kind of graph structure, and a node is going to activate or do something based on what its neighbors are doing, right? So if I'm trying to decide whether I should buy an iPhone, I might be looking at how many of my friends have iPhones, playing with their iPhones, deciding that I like the iPhone and I want to buy it. So this is the model that was used in a lot of these different works. It was named the linear threshold model by Kempe, Kleinberg, and Tardosh. There's all sorts of other models, but this one is the closest to us. What it says is that the utility of a node is proportional to the number of its active neighbors. So the key point here is neighbors. This one is active, here's its neighbor, and so his utility is going to be 1. And as long as the number of active neighbors increases beyond its threshold, then he'll turn on. Okay, so it's just like our model, except in our model it's components, and in the linear threshold model it's neighbors. Okay. There's this other set of modeling that's very prevalent in other fields called direct network effects. So probably the easiest thing to do is just to look at what, okay, so here's my cursor, Metcalfe's law. So Metcalfe was actually the inventor of Ethernet, and he came up with this law, which is basically exactly what Katz and Shapiro were talking about in their paper from 1985. What this law says is that the utility that a user gets from being part of a network of n users increases with n. So think of a fax machine. If I buy a fax machine and I'm the only one who has a fax machine, its utility is pretty much nothing because I can't fax anyone. But if there are n other people who are using fax machines, then I can all of a sudden fax n people and my utility increases with n. So that's what Metcalfe's law says, and this is actually taken directly from this Katz and Shapiro article from 1985, which was written around the beta VHS wars. What's really interesting, I think, about this is that the way that they describe these network externalities, the utility that a given user derives from the good depends on the number of other users who are in the same network as he or she. When they say network here, they don't mean graph. They just mean people that use the protocol. So it's just a count of the number of people that use the protocol. Okay? And we also see this in marketing. There's this BAS model, which is a model based on differential equations that also predicts the count of the number of people that use the protocol based on the number of people in the population. So the point is that we have these local network effects that depend only on your neighborhood, and then you have these direct network effects that really just depend on a count of the number of people that use the protocol. So in this picture, the utility of this guy, if we were to think about direct network effects, would be 5 plus 3. It would be 8. In our setting, what we're looking at is how many people can you actually reach through the network. Okay, so we can think of this as sort of in between the two models. Questions? Okay. So I don't want to spend too much time on this because I only have 45 minutes. The point of this slide is to say that our model looks a lot like the linear threshold model. The only difference is the utility function, actually. It's exactly the same. However, algorithmically, it looks really, really different. And you can see here some of the different formulations of the problem, where this formulation, the one that we solve here, which I'll tell you exactly what these parameters mean in a second, is extremely hard to solve in the linear threshold model. So the setting that we actually work in is, the problem is much, much harder in the linear threshold model. Whereas the famous algorithm of Kempe, Kleinberg, and Tardosh, which gives you an order 1 minus 1 over E approximation, this is a greedy algorithm that's based on submodularity. It just doesn't work in our setting at all. There's no submodularity that we could find. And so we couldn't actually do any of this. So part of the reason that this paper took so long for me to write was until I had met Zhenming. Didn't know how to think about the problem at all because it doesn't look like the other diffusion problems that we're familiar with. So what I want to do is give you some details on why this looks so different algorithmically. Okay, so I'm going to focus on this. Okay, so we have this problem. We have the graph and the thresholds, and we want to find the smallest set of early adopters that can cause everyone in this network to adopt. So here's our main result. Our main result is approximation algorithm, and it's parameterized by these things. Log v is the number of nodes, log of the number of nodes in the graph. R is the diameter of the graph, so that's the length of the longest path in the graph. However, this is a worst case guarantee. The actual algorithm doesn't use the longest path in the graph. It can just be the average path length in the graph. Now, if we think about internet graphs, the longest path in these graphs is around 11, and the average path length is around 3.5. So this number is actually not very large. So we're talking about a graph of about 40,000 nodes with a longest path length of 11. Okay, so R is very small. K is the threshold granularity. So what is K? K is just, in this example here, we have 5 thresholds, so K would be 5. It's the number of thresholds that we can have in the problem. We'll talk about that in a second. We have a bunch of bounds that explain why all these parameters are here. So the log v is here because of a hardness result. This is harder than set cover, so we have this log v here. This order R is because we use a particular approach that incurs this order R that we cannot avoid. So there might be other approaches that don't incur that order R, but because we use this approach, we have this order R. And finally, we use a linear program that has an integrality gap of size k. So that's where the k factor comes in this algorithm. Okay. One more comment about the k factor is so you might imagine you could have a number of thresholds that are available. It could be exactly equal to the number of nodes in the graph. And then this would be a trivial approximation, and it would be useless. But what we can show is that if there's some when we think about this problem, we don't think of each node having a different threshold. We can sort of think of them being, roughly distributed like this. So you can have sets of thresholds like this, 1 plus epsilon, 1 plus epsilon squared, 1 plus epsilon cubed, and so on up to 1 plus epsilon to the log b. Right, so if you imagine that the thresholds are chosen from this set, then you can show that if the problem is insensitive to perturbations of size 1 plus epsilon in the threshold, then this k becomes logarithmic, and our approximation ratio becomes just log squared times r. Okay. So, and in fact, I think a problem that is sensitive to perturbations like this in a huge way is probably a malformed problem. So that's why we don't feel that this k is a big problem. Okay, good. So I have 20 minutes. I'm going to try to show you how we solve the problem, because I think that this will give an idea of why this looks so different from the standard diffusion problems. So our algorithm has 4 steps. The first step is a linearization step, and it gives us an integer program. This is the part I'm going to show you in this talk. We get this really short, very cute integer program that is about 4 lines long. Unfortunately, we can't use this integer program because it has a huge integrality gap. This should not say log, actually. This is an order v integrality gap, sorry. There's no log there. So this is a huge integrality gap. And then we change the integer program, and we reduce the integrality gap down to here, and then from there we do randomized rounding. Okay. So in the short time that I have, I'm not going to be able to go into the details of all of this. I'm just going to focus on these 2. This will give you an idea of why our problem looks so different from the usual diffusion problems. Okay, here's our problem. So remember, our seed set are the nodes that turn on first due to some sort of external incentive. And now I need this notion of an activation sequence. Okay, so an activation sequence is just the order in which these nodes activate. So for example, what I'm showing here is that we had, all of these blue nodes are going to activate, here. And then after them, the red nodes will activate, and so on. And then the green node will activate, and it'll appear in our activation sequence. And then the purple node will activate, and it'll appear in our activation sequence. Okay, so that's all an activation sequence is. If 2 people can activate at the same time, just make them activate one after the other in some arbitrary order. Okay, this is the tool we're going to use to solve this problem. So first of all, why is this problem complicated? So let's look at the example of the purple node right here. Here's a purple node. So if we look at the graph in this state right now where these red guys are active and the blue guys are active and the green is not, the utility of this purple node is 7, right? It's small. Okay, so now you can guess what's going to happen. What happens when I turn on the green node? His utility jumps in a huge way, right? Because now he's connected to all of these blue nodes, and so now his utility is all of the red plus all of the blue plus the green. So his utility jumps in a huge way. So why am I telling you this? The point is that the utility of a node is extremely dependent on what happens really far away from it in this problem. And that's really annoying to deal with when you're trying to encode it with a local constraints and use an integer program. Okay, so what we're going to do is we're just going to avoid the problem completely. Okay, we're not going to let distance nodes influence other nodes. And this is how we're going to do it. We're going to use this thing called a connected activation sequence. So here's what that is. So remember what our activation sequence, it's just the order in which nodes activate. So here we have nodes activating. But this is a connected activation sequence in the sense that every time a node activates, it's connected to all other active nodes. Right? So now we can turn on this blue node, it's connected to all the active nodes. The green node is connected to all the active nodes, and so on. And so I can activate this graph in a connected way. Okay, so that was an example of a connected activation sequence. Okay, so here's the beautiful thing about a connected activation sequence. Here's my activation sequence, and my purple node turned on right here. Right, he turned on at the 15th time step. So I can actually tell you exactly what his utility is. He turned on at the 15th time step, his utility is 15. Right? So now actually at every time step, the utility of every node can increase by at most 1. Right? The utility of every node that activates. So now we know the node's utility just by looking at its position in the sequence. And so we can actually use this to solve the problem. We no longer have to worry about this exploding utility when one node turns on. Okay, so here's what we're going to do now. If I draw the thresholds of each of these nodes, so this guy's threshold is 12, this guy's threshold is 8, and so on. I see that this utility, this node, purple node turned on at the 15th step, so his utility is 15, right? Here's its threshold. So I can immediately conclude that the reason that the purple node turned on was because he wanted to turn on, right? His utility was higher than his threshold. He's happy and he's not a seed. right? He's not an early adopter. He's a node that turned on spontaneously on his own. But if we look at this green node, we can see that he turned on at this time step, which is before his threshold in this activation sequence. So we immediately know that this node has to have been a seed, because otherwise he couldn't have turned on at that step in the activation sequence. Okay, so in this particular activation sequence, I can immediately tell you who corresponds to seeds. It's these blue nodes that turned on before the blue threshold, and then this one green node, and everybody else turned on spontaneously. Okay, so the insight that Zhenming had was actually, let's stop worrying about seed sets, let's just look at activation sequence and assume they're connected. Okay, and this way we can immediately derive the seed set directly from the activation sequence, and we no longer have to deal with any of this complicated mess. Yep.
So we need to get a connected seed set?
Yeah. Good. So if we have a connected seed set, you might ask, is that horrible? Do we lose a lot in the approximation ratio? And actually, it turns out that we don't. So we have a theorem that shows that a connected seed set is actually a 2 approximation to the optimal seed set. So even though this seed set the seed set that we chose here comes from a connected activation sequence, we can show that there exists an activation sequence for the optimal seed set that seed set is going to be at half the size of the one that we extract from here, at most. Yeah.
So you're not requiring that the seed set itself is connected,
Yeah.
but that it's part of a connected activation.
Yeah, exactly. And actually, this is a 2 approximation. It gives us this really cute IP that's like, here it is. It's 4 lines long. So when I saw this, I was like, yeah, we solved it. It's so cool, but we're done. And we weren't, actually, because this has a horrible integrality gap, and it behaves really poorly. But it's very cute and short. Looking for connected activation sequences gives you a 2 approximation. However, in order to round it, we needed to look for connected seed sets. So all the seeds had to be connected. And when you do that, you have an order R approximation in the radius, and that's where we got the R in our rounding algorithm. So we're not able to get rid of the connected seed set in the rounding, but we were just in the linearization. Okay, so that's where the R comes from. Okay, so now I'll just quickly, any more questions on this? Yeah.
So in that problem, do you care about the number of nodes of the seed set?
Yeah.
Or to identify the seed set?
So we can identify the seed set because we will find a sequence, a connected activation sequence. We will return a connected activation sequence like this, and then I can just do the trick that I told you to extract the seed set, and then I'll be able to tell you exactly who they are. So we will find the seed set. We won't just tell you the size. We care about the size, but we can return the seed set using exactly this.
It seems that you care about the seed set more than the size, right?
Yeah, sure. So you're optimizing for the size of the seed set. You want a small seed set, but I need to know who the seed set is, or this is not a useful exercise. Yeah. Yeah.
So in your modeling, you're looking at the time function. So how long does it take for the to diffuse? Because your sequence, you
Yeah.
have in the sequence.
Yeah.
But it seems to me that time would be an important part. If you want, for instance, you don't want this to be actually linear in the number of nodes in the linear, because that would be very long.
That's true. We completely didn't deal with that. Yeah, that's true. I think in practice it's not going to be. And I can show you something at the end, which may convince you that it's not too long. But yeah, we didn't deal with that at all. Here's the integer program. Okay, so we have these variables x, I, t. I and t run from 0 to the number of nodes in the graph. It just encodes the activation sequence. So xit is going to be 1 if node I activates at time t. Okay. Now our objective is to find the smallest seed set possible. So what this summation does is it's going to be 1 if I is a seed. So what we're doing is we're counting up the xits up until the threshold of the node. Right? So we're counting, for example, for the green ones up to here. And we would find xit equals 1 at this position. So for the green node, so then we would actually see that that node is a seed. So that thing counts up the number of seeds. This thing counts if I is a seed, and then we count over all I, so we know the total number of seeds. We have these 2 permutation constraints that the xits sum to 1 in the rows and the columns, so that the activation sequence is a permutation. And then finally, one last constraint, and what this constraint does is it ensures that the activation sequence is connected. Okay, so here's how it does it. So if xit is 0, then we just need some positive number is bigger than 0, so that's always true, so we don't have to care about that. So this constraint only matters when xit is 1. Okay? So if xit is 1, we need to make sure that at least one of the neighbors of I is on by the time that, that I activates. So what this thing counts, what we're counting over is all the neighbors of node I. These are his neighbors. And we're just making sure that they're activated before time t. Okay, so if as long as one of his neighbors is on before time t, then we're happy and I can turn on. That's it. That's the whole integer program. Okay, so maybe after 1 o'clock I'll show the proof of this, which I think is the cutest proof on the paper, but I'm not going to do that now because there's not a lot of time. Okay, let's see the proof. Okay, so great. So that's what we do. We get to that 4-line IP. We have to make our IP more complicated because of its horrible integrality gap, not log v, but actually v. This one has an integrality gap that we were not able to get rid of, and then we use randomized rounding to finally solve the problem. One thing that is actually interesting and nice about this, I think, is that we actually ran our integer program, the 4-line one, on some smaller graphs, and it actually does work and find good solutions. So it could actually be a good starting point for heuristics, but we didn't explore that too much either. Okay, great. So now we're going to be really cynical. We'll put on our cynical hats and we'll say, okay, great. So you just showed me that there's this nice model where nodes are going to upgrade to this protocol because they can communicate with a lot of their neighbors, and that's going to be a great reason for them to adopt the protocol. So actually, this is the bare minimum of what you need. What a lot of the skeptics say is like this quote over here. They're saying that if there's actually no commercial value to adopting the protocol, it doesn't improve my business in any way, then why would they actually do it? And that's one of the reasons why a lot of people are very skeptical that things like BGP-SEC will be deployed. Okay, and also skeptical that IPv6 will be deployed, but it looks like it is actually happening now. Okay, so what we did in the next work with Michael Shapiro and Philippa Gill is we showed that there's actually something very particular about BGP-SEC that you can exploit to show that ISPs might actually want to use it in order to attract more revenue. Okay, so let me show you what that idea is, and this is particular to BGP-SEC. Okay, so BGP-SEC is a routing protocol, which means it influences routes, right? If you're trying to secure routes, you should probably choose the routes that are secure in some way, and so that's going to influence the routes that you choose. That's the first point. Second point, the routes that you choose influence where traffic flows, and the third point, that traffic flows influence the revenue of an ISP. They make money by charging their customers for carrying their traffic. So if you get a lot of customer traffic, you're going to get a lot more money. Okay, so here's the idea. So we have here Sprint, and he wants to route to BU, and he has 2 different ways. And let's assume that these are equal cost paths, and for some reason ISP1 is preferred according to some tiebreak. Okay. So if BU is the customer of ISP1, BU will have to pay more money to ISP1 to receive this traffic from Sprint, because the payment is done by volume. So now, what happens when we deploy routing security? So if these nodes get secure, now when Sprint has the choice to route to BU, it has 2 equal cost paths, as we showed before. But now what we assume is that we're going to assume that he's preferring the secure path. So what happens in this case is that the money that BU was originally paying to ISP1 goes to ISP2. And the result is that ISP1 loses money. Okay? So the idea here is that we use this fact that the traffic will move towards the secure part of the network and then sort of drain out of the nodes that are insecure. And that's going to create an incentive for the nodes that are insecure to actually adopt the protocol. Yep.
So Sprint chooses the path, but ISP1 charges BU?
Yeah.
Doesn't that somehow...
It sounds weird, right? Yeah. So he gets, so think about you, your service provider. When you watch movies, the traffic is coming from, let's say, Netflix, right? But you're paying to receive it. So Netflix chose to route to you, and you're paying to receive the traffic from Netflix. So the way that the cost structure in these networks works is that if you're a smaller network, you pay your provider both to send and to receive. So if BU is to send to Sprint, it would pay. And if BU is receiving from Sprint, it would also pay. So the way that the payments work are not based on the direction of the traffic. It's based on how big you are. So if you're, like, for example, Harvard will pay its providers to send and receive. And then the provider of Harvard might pay a bigger provider like AT&T to send and receive. right? So there's this hierarchy of who pays who, but it's not based on the direction of the traffic. Okay, so here it would be the case that he would pay. Okay, so that's the idea we use. Now, IPv6 doesn't control routes quite in the same way. There might be a way to do it, but it doesn't quite work in the same explicit way that BGPSEC actually controls route, because BGPSEC is actually a routing protocol. So we have this hope that BGPSEC might actually make it a little bit easier to do adoption. Okay, so what we did in this paper is a prescriptive strategy to drive BGPSEC adoption. So there is no set of rules that say this is how you should actually deploy BGPSEC. What we tried to do in this paper was to give guidelines for how the protocol should be deployed. What we said was that secure ISPs should prefer secure paths. We make this only a mild preference. We say that only if they have equal cost paths before security was there, they should prefer the secure route if it's there, if it's available. So like in the example I showed you, there were 2 equal cost paths, and we should require the secure node to prefer the secure path. So that's the first part of our guidelines. By the way, none of this is actually written in the standard about what secure ISPs should do with secure routes. It just says do whatever you want with your own local policies. Okay. The second point is similar to the previous stuff that I was talking about. Again, we need early adopters, and then let the market pressure convince the rest of the nodes to do the adoption themselves. And finally, there's one other property that we use here in this work. What we're doing is we're exploiting the very particular structure of the internet graph. The internet graph has around 40,000 nodes. 85% of these nodes are what we call stubs. 85%, okay? And stubs are networks like BU, where they're edge networks. You can think of them as customers of internet service rather than providers. They just send and receive traffic, but they don't carry traffic for other networks. Now, it turns out that you can run BGPSEC at these nodes in a very cheap way. I'm not going to get into the details, but roughly it amounts to these nodes, because they're sources and sinks of traffic only. So basically, think of a path. These nodes can never be anything but the first or the last node on the path. So they never carry traffic through them. So what that means is if they're the first node on the path, they should send out a BGPSEC message. But if they're the last node on the path, they never actually send out messages to anyone, because the path stops there. They don't tell anyone what path they're using. And so they don't actually need to run BGPSEC when they're the last node on the path. So the result is they really only need to run BGPSEC when they're the first node on the path, and that happens very rarely. Right? So think about all the paths in the graph, all pairs paths. You only need to run BGPSEC when you're the source of the path. Okay? And because it's only for that small fraction of paths, the actual protocol can be done much more cheaply. You can do it possibly in software as opposed to hardware. And this is actually in the standard, to have these networks run this cheap version of BGPSEC. So what our strategy says that when a large network adopts BGPSEC, they should also, sorry, there's a mistake in the slide. Whenever a large network adopts BGPSEC, like this ISP, he should also force his customers in some form or another to run BGPSEC. And there's more details of that in the protocol. But the idea is that that's going to be cheaper, because they're just edge networks. OK, so here's our model. So remember, now this is the big difference between the two papers. In the previous work, we said that the utility of a node was how many people he can speak to using the protocol. In this work, we have a completely different model of utility. The utility is the number of routes that you carry towards your customers. Right? So just like I showed in the figure before, imagine that this is BU. BU pays ISP-N for service. The utility of ISP-N that he derives from BU will be proportional to the number of people that use ISP-N to route towards BU. Okay, and we do this over all customers of ISP-N. So basically, it's the amount of traffic you transit for your customers. So all the traffic that comes into you that goes out towards customers, that's going to be your utility, which is very different from what we had before, which was a count of the number of nodes that you could actually reach using the protocol. This is really a count of the traffic that you transit when you're using the protocol. Okay. And then things proceed very similarly to how they did before. Each secure ISP has to choose if it's going to become secure. The way it's going to do that is it's going to look at the world before it was secure and look at the world after it was secure, see how much more traffic it got after it was secure, and if that more traffic was greater than the threshold, then it will adopt the protocol, and if not, it won't. Okay, so the idea is it sort of imagines a world where he deploys the protocol, sees how much his utility will increase, and if it increases enough, he's going to adopt it, and if not, he won't. Okay, so This model is a lot more complicated than the previous one. Before, we were just counting number of active nodes. Here, we're counting traffic transited through a node, and we're trying to project what that traffic's going to be in a future step after other people have taken their actions and so on. So you can imagine that we did this problem in simulation. We didn't actually solve this problem algorithmically because we couldn't. It was too complicated. Okay, so that's the model. Yeah.
So it's theta percent, so it's a relative.
Yeah. So it's basically like if you look at it's like utility before and adoption and utility after. So utility after should be greater than 1 plus theta of utility before.
Right, so I'm just wondering, why is a relative thing the right thing to do?
So I believe it's absolutely the right thing to do. So the reason is because if you're a large, so if I was to count the number of nodes, and then like let's say I was to use a non-absolute number, so let's say I was to use an absolute number. So I say that if you get 5 more customers, then you are going to adopt the protocol. So if you're a huge network and you have 100,000 customers, getting 5 more customers might not make a difference for you. Whereas if you're a tiny network, getting 5 more customers is going to make a huge difference to you. So what we're trying to do is that this is a relative increase because we should get a lot more traffic than what you already have. So if I have a huge amount of customers and I adopt the protocol and I get 20% more, then that's going to be a lot more important than getting than saying that I'm going to get 5 more customers. That doesn't.
So that it makes sense. I guess another way of asking is, is the cost of adoption also kind of proportional to these things?
That's a good point too. Yeah, so it is, because you need to think of these networks as having a huge number of routers. So the amount of traffic and amount of customers you have is going to be proportional to the number of routers and devices that you have in the network and how big you are. So if you're a tiny network like BU, you might have like 4 or 5 edge routers, whereas if you're AT&T, you have thousands, right? So the cost of adoption is going to be a lot higher for AT&T than it would be for BU. Yeah. Okay. So, so we couldn't really prove much about this model. You can possibly see why. And in fact, this paper was written before the paper was Zenming, so back then we didn't even know how to solve a simple problem before I had met Zenming. So what we did was we did simulations. What we do is we simulate the dynamics of adoption over graphs of the internet. These dynamics were quite complicated because at each step we needed to have each ISP compute its total change in traffic if it was to adopt the protocol. So in order to do this, this is actually an order V cubed simulation, so it was quite complicated and we had to parallelize it on a cluster. Bottom line is, we showed that if you have just 10 nodes adopting the protocol, we could get 85% of the network to adopt the protocol. So if we required 5% increases in traffic, then only having 10 early adopters was enough to drive 85% of the network to adopt the protocol. And the reason for this is, here, I'll show you a simulation. This is actually an excerpt for the simulation. What's happening is that as more nodes adopt the protocol, they start stealing traffic away from each other, and these paths start to get longer, so you can see. Right, so it jumped over there. So let me run that again. The idea is that you start out with these small diamonds like what I showed you before. Okay, so we start out with these small diamonds. The traffic jumps to that side of the diamond. Then the one who lost the traffic turns on to get it back. And then now, because we have more secure nodes, we can actually get a longer secure path over here, and the traffic will jump again. The reason that this node turned on spontaneously is because it's an edge network, and we required edge networks to turn on when their providers to turn on. Okay, so the idea is that these diamonds, there's actually a lot of such diamonds in the graph, and they get progressively bigger. So we go from diamonds of size 1 to diamonds of size 2, and so on. We actually see bigger and bigger diamonds until 85% of the network deploys. Most of the time where the process stopped was when we didn't have enough diamonds to actually drive it. Yep.
So what's to stop the guys in the middle of the diamond looking at each other and going, well, if you switch first, you're going to steal my traffic, and then I'll just steal it back, and we'll both not have gained anything. But we'll
so there's
how much money it costs to.
There's not a lot of reasoning that I can give you why they don't do that. But I can show you, for example, a graph of the utility of these nodes as the simulation progresses, and this kind of answers Kobe's question. This is 30 rounds of simulation. So again, the number of nodes in this graph is 37,000 in this particular simulation. And it terminates at around 30, at 30 steps. The green and the red, I think, are right. So remember these two nodes, the ones that were on either side of the diamond that you said should communicate with each other and decide not to adopt these two?
Yeah.
Those two? So I'm showing you that in green and red, that's their utility. Here we go. This is their utility as the simulation progresses. They actually sort of both get utility for a while, even though one steals back from the other. Sort of, it's part of other paths, and they get stolen over to him. What you end up seeing is when the simulation terminates, is that these nodes finish the simulation being secure. This node finished the simulation being insecure. And so what you end up seeing at the end is that the utility sort of flattens out. There's this period where the traffic's moving around a lot. The ones that are secure can get a lot more traffic than the ones that are insecure. And then eventually everyone becomes secure and everything sort of stabilizes, except for the nodes that are insecure and they've lost quite a bit of traffic. And so this is sort of characteristic of what you would see at the end of the simulation. You get this period of gain and then it flattens out.
But interesting, like this red and green guys, though, they look like they're under the threshold, right?
Yeah. Yeah, so this is a, yeah. So if you look really far in the future and you assume everyone adopts, you assume that you got no utility at all. But then on the other hand, you might want to integrate this curve, for example, and say that you got some utility there. But yeah, I think the main point of this work was to show that, that this was possible, that there was something special about this protocol, that because it controls routing, it can actually direct routing in ways that you want. And it can be used as a mechanism to drive adoption. Basically makes your network more competitive relative to your competitors. Okay. And that's really it. That really it. So we looked at this problem in two different ways, and of course one approach feeds into the other, because when we looked at the second approach with this traffic shifting, we really had no idea how to choose early adopters, so we just did the simplest thing possible, which is choose the big nodes, which is actually what they do in practice. With these policy groups actually do look at, like, let's go to big networks like Google or Amazon or AT&T and get them to adopt the protocol. So that's what we did there. In the first one, we actually have an algorithm for doing this. Just one final aside, this started out as a tale of two protocols. IPv6 has been in deployment for 15 years. And what's really interesting and exciting is that now, after 15 years, the core of the internet basically speaks IPv6. And what's happening now is there's a need to drive demand from the edge of the network, like your laptop needs to now start speaking IPv6, and it doesn't usually. So the routers in the internet speak IPv6, but your laptop doesn't. Or it does, but it's turned off, actually. Your provider doesn't give you a v6 address most of the time. With BGP-SEC, BGP-SEC doesn't work in your laptop. It works in the routers in the routing protocol. And so there's a couple of things. First of all, this is not deployed yet. It's still being standardized. But there's some cool things about this protocol. For one, the edge networks are actually, it's very easy to run BGP-SEC in the edge networks, like I talked to you about before. And the edge networks are edge networks as opposed to your laptop. This notion of the fact that it controls routing can actually potentially push some of the traffic towards the more secure nodes, which is not something you could do with v6. So we do believe that there is some hope for BGP-SEC relative to some of these other protocols. But really the point is, in all of these protocols, the real stumbling block is the fact that in order to actually use them, you really need paths through the network. And that's very hard to get in a distributed protocol where each node is run by a different organization and there's no one that can say, like, you now must go deploy this. Okay, so that's it. Thank you. Let me put my shameless plug back on.
There seems to be an inherent flaw of BGP-SEC that after the transition, everybody actually returns to their original revenues, essentially.
Mm-hmm.
So as a community, there's no incentive to move to this protocol, because eventually you only pay for the employment and you don't gain much from it. In the long term, the overall gain is
So I guess the argument that I would say back to that is that you actually get a more secure internet, which is really the goal.
So exactly, this is what I want to say. So if there's no economic incentive for security, and I guess this is the main question, if there is the economic incentive for actually reaching security. If there's no such incentive, I don't see that the argument is convincing the local argument.
Yeah, so I mean, I do think that there is a incentive for security in the long term. I just think that getting there is the difficulty. So this is meant to sort of argue that in the short term there is some benefit, and in the long term you will get better security than you have now. There is, a lot of push to actually get these things deployed. Like there's a lot of government money involved in these things. So I think that network operators do believe that there is an incentive, and what this work is doing is saying like maybe there's actually something along the way, because when you think about these protocols, so actually if we talk about V6 is has a very strange set of incentives. What it's meant to do is completely replace IPv4, right? But in the course of the transition, what happens is that every device has to speak both IPv6 and IPv4, which means that it needs to use IPv4 addresses and IPv6 addresses. So you haven't saved on any addresses at all, and that's the whole purpose of the protocol. So there's really like, in the transition, there's very few incentives to actually use the protocol. The incentives to use V6 are, at the end of the deployment process, we all stop using V4, and we all have all these addresses, and now we're all happy, right? And in the BGPsec model, it's actually a little bit better, because as the protocol is being deployed, if you choose secure routes, you might get some security benefits, you might get some traffic. So, but anyway, you're right. I mean, actually deploying these things is very difficult, because until you get to the end game, it's very, very hard to convince people to go there, even though it has been happening, for example, with V6, just through a lot of PR and a lot of like, advertising, pushing network operators, regulation, things like that. Yeah.
If you run the algorithm, the one which I'm making,
Yeah.
on the internet, graph?
So Zenming and I were not good enough to use these numerical optimizers on a graph that large, because there's all this tricks. Like, it's really cool. There's this whole body of work on how to use these optimizers, because you need to understand the underlying algorithms and put your input. Because what we did was at the beginning we had 20 nodes. We could do it on 20 nodes. And then we read some web pages, and we all of a sudden jumped up. We could do it up to 300 nodes by just changing the input matrix. And we weren't good enough to, we didn't spend enough time learning all these tricks to actually push it further. So
Feeling this went up to teacher optimization.
yeah, you need to know the exact algorithm that the optimizer uses, and exactly how to put the input. We put in a matrix that was much bigger, size, we squared the size of the matrix, and then it became super fast. It was, yeah, things like that. So there are people who know how to do this, but we don't. So we have 2 minutes. What do we do?
Show us the proof.
In 2 minutes? No.
No?
The proof is 3 slides. There's no way. No.
All right, let's thank Sharon.
Thank you.